Okay, so next we're going to get a definition of a unit vector. So remember in math, unit typically means the number 1, just like with a unit circle. That's a circle with radius 1. So very similar with a unit vector. So definition, a vector whose length or norm is 1 is called a unit vector. Right, so a vector whose length or norm is 1. And we actually can turn any vector into a unit vector, or we can create a unit vector from any other vector. And so we actually have a process for doing this called normalizing. So you may have heard of normalizing a vector. All right, so the process of creating a unit vector, I'm going to use U for unit, from another vector V. So the process of creating a unit vector U from V is called normalizing V. And we say U is in the same direction as V. And so this part of the definition is important, in the same direction as V. So you'll often say, find another vector, or C, find another vector that's in the same direction as V, but is a unit vector. So find a unit vector in the same direction as V. So that would be normalizing V. All right, let's look at an example. All right, so what we want to do is find a unit vector in the same direction as the vector V. And V is -1, 2. So this is what we used in the earlier example in the previous video. All right, so how would we do that? Well, to normalize it, what we would do is do 1 divided by the norm of V, and then multiplying that by V. So from the previous example, we found that the norm of V is the square root of 5. So 1 over the square root of 5 times the vector V, -1 over root 5, 2 over root 5. All right, so this is our vector U, and this has length 1 and is in the same direction as the original vector V. So U has length 1. So if I were to draw these on a graph, the vector V was -1, 2. So this would be V, and then U would be a smaller vector that has length 1. But it's in the same direction. Okay. All right, so let's get a quick little note here. Do you remember these? E1, to en. So remember, these are column vectors of the identity matrix. So there's 1, 1, and then the rest are zeros in each of these column vectors. These are called elementary unit vectors. All right, so the columns of our identity matrix are called elementary unit vectors because they each have length 1. All right, so let's look at one of these. Let's look at E sub j. So I wanted to look at the norm of E sub j. And remember, to find the norm, it is the square root of EJ dot product with itself. Which means we need to take the transpose of this times the original. So I'm going to draw a weird big square root so we can fit this all in here. Transpose, so we're going to have all zeros. In the jth position, we're going to have a 1, and then we're going to continue with our zeros. And then same for the column vector version. All right, so what happens when we do this dot product? All the zeros are going to match up and the 1s are going to match up. So this is going to be the square root of 0 plus a bunch of zeros plus 1 plus 0 plus more zeros. Which is just 1. So every single one of these elementary unit vectors has length 1. All right, so what if we wanted to figure out the distance between two different vectors? Let's talk about how we would do that. So distance between vectors u and v. All right, so remember our parallelogram rule, right? So if we have some vector u, I'm just kind of drawing these floating in space, and another vector v, we can figure out u plus v by just drawing another u right here, and another v here. The vector that goes straight through the middle is u plus v. But what if I wanted to just figure out the distance between u and v? What would that look like? So this is my u. This is my v. The distance between them would actually be u minus v. Or that's the vector between them. So to find the distance, we would just need the length of that vector between. So we now have a new definition. The distance between two vectors, u and v, is going to be the norm, or the length, of u minus v. All right, and so we'll do an example in the next video.